All right, welcome everybody to today's Accendo Reliability webinar. This is Fred Schenkelberg. And today I'm going to talk a little bit about, which is a pretty broad topic, reliability and maintenance. It started with a question a couple of months ago I received. It was from a young engineer that was starting as a role as a reliability engineer in a factory and a facility of some sort. And she was curious if she noticed that a lot of the writing I do and a lot of work I do is from my background in product development. And she was wondering if that kind of reliability engineering was relevant for a factory or a plant setting. And I had to agree, it's different to some extent, yet there's a pretty good amount of overlap. And so I'm going to talk about what I want to talk about today is the one of it is some of the difference, but also the relationship between the reliability engineering work and the design work that goes into a product or a system and the role that the maintenance team plays in that development and vice versa. What can the development team do to support the maintenance team and back and forth? And so we'll cover a couple of different basics, but that's where this topic came from, was a question that came up a couple months ago. If I get my cursor, there we go. Now, one of the things, if you're designing a product that is strictly product reliability, and if it fails, it's done, right? It doesn't work anymore, or it's degraded to the extent where it doesn't have its full functionality. We don't usually then talk about downtime. Downtime is when you're actually getting the wrench out and go fix something, right? And so I'm going to explain the details a little bit, which should be obvious to all of you. But the idea is that reliability engineering, when you're in a facility role, or you're working with a product that has repairable features to it, you're making something that goes into a factory or a vehicle, for example, downtime, or when it's not working, when it's needs repair, then it's a where the system or service you're offering is not available, it's down. And so there's a different bit of terminology when you're dealing with repairable systems. And so in reliability, when we are talking about a product that in its reliability performance, and we could have, recurrent failures or multiple failures for one system and they get repaired, but we usually think of it as the time to failure distribution and Weibull analysis and stuff like that, time to first failure. Or we try to make it so that there's very few failures, if any, for some duration, or a chance of few failures over some duration. But that's only part of the story. If we only work on creating a product that doesn't fail, that's only part of it. Now, the repairing side also has a role to play in creating a product that avoids or minimizes downtime. And that's how long does it take to repair it? And so there is an interplay between these two concepts, or these two roles that we have in our organizations. One is the design of a system, and the other is the maintenance of the system. And so let's explore a little bit where reliability activities, or folks like ourselves that are interested in this and trying to create a product that minimizes downtime, would find a role. What would we be doing? And so we'll talk about some of that stuff. Excuse me. But here's a question for you: is if you're making, let's just use a vehicle, for example. Say I have a passenger vehicle, which I think hopefully all of us are familiar with at least what its function is and its use cases. What's the right balance, right? I think early cars had multiple spares and all kinds of toolkits that came with them, because fixing daily and tuning up daily or replacing flat tires regularly was just part of the process of having a vehicle. Now, was it worth the effort versus feeding a horse and keeping your carriage in good shape? That was a debate individuals had to make at the time. And there was a bit of a cool factor having a car when nobody else did, but that wasn't for everybody if they had work to get done, work to do, for example. So eventually, the amount of maintenance required for the ownership of the vehicle changed and evolved over time. And some cars are better than others today. And that balance continues to change. We haven't made a vehicle yet that requires no maintenance whatsoever, although you probably could point to the lunar landers and satellites and what's the ones out on Mars, the Perseverance and I think Endeavor and a handful of other fancy names. It's not like they're going to run a technician up there to change a tire. But the Mars rovers, thanks, Sean. But I fully suspect that some of it is that they probably, and I'm just guessing at this point, that they probably have some software systems that can be updated or altered, or they have alternate ways to get a function done if the primary system doesn't work. I have to imagine that there's some redundancy in those things and configuration on the fly. May be totally wrong. They may have just made a really reliable device and counted on that. It's not clear. But what's the right balance for your product, for your facility? What's the right place to go? All right. So let's go into a bit of definition. Now, one of the questions I ask students regularly is, go find an advertisement that uses the word reliable or reliability. And some of you have seen me do this before. But the idea is that most people, at least in the English language, and I've heard anecdotally from some friends that in the Spanish world also, Spanish language world, is that reliability means trustworthy, right? It means that you'll show up at the meeting on time and you've been counted on. And if you say you're going to do something, you go do it. And it applies to products also, is that if your product is reliable, it will, like a passenger vehicle, will get you to the store and back. And you can count on it as a mode of transportation for you. And you don't need a whole bunch of tools to make that happen. You won't be broken down on the side of the road. So availability has a similar set of unsuredness, I guess is the right word, or multiple understandings. In common language, it has a slightly different meaning than it does the way we use it. And the issue is that we have to be very clear what we mean. Right? Availability is not the same as reliability, right? And some of you know this, especially those that are dealing with like system effectiveness type measures, is reliability is it'll go to the store and back. It can make the trip. It's good for the mission from a military context. Availability is that it's ready to go. And it's sorted out and it's possible for it to start and go to the store, and it's not in the shop. It's not getting an oil change at that moment. It's battery hasn't drained out. It's ready to go. And that is one way to think of availability. Let me dive into a more common way, and then I'll ask you if you have other ways to define this. it's basically just a ratio of when's it ready up? When is the system running, or is it ready to run? It doesn't actually have to be running, but it's ready to go and start producing widgets or run down to the store over the total time that it's available to or expected to be up and running or available. So my car sitting in the driveway has been available all week, as far as I know. The handful of times that we went to it to make a trip, it started and then it was reliable. It got us to where we wanted to go. So the total time was 7 days, which is what, 169 hours, if I remember right. And it had no downtime during that period. But if I had an hour where I had to take it to a shop, or I think one of my vehicles a couple of weeks ago, I was filling up the tires. I had a compressor out and I was up adding some air to the tires. Now, technically, nothing was flat and it was still serviceable and it could have gone off and run, but I was out doing some maintenance on it. Maybe total time, let's just make it an hour. But I had an hour when it was not, wasn't ready to run, for example. And that's 1 hour over 169. The total time, meaning both the uptime and the downtime. Now, there's all kinds of other ways of measuring availability. And so I'm going to hand it over to you up in the chat window. What's the way that you would measure or calculate availability for something maybe that you're working on? Allows me to get a sip of water too. It's not a trick question. And you know, I don't like MTBF, but that's a common one. MTBF over MTTR, mean time to repair, plus MTBF, right? Yeah, basically it is the ratio of when it's working and doesn't. And it's a way to go about doing this. I've also heard of availability as operational, what your actual measured time is. I've seen that done in factories plenty of times. But there's also theoretical. The equipment manufacturer says, well, we don't know exactly how many shifts you're going to run, so we don't know what your total time is. But theoretically, if you have perfect maintenance, that those wrenches are right there and the spare parts are right there and the diagnostic time is perfect, is zero essentially, then if we only count the wrench time, then you could get this kind of availability. Yeah, power generator uptime. Yeah, Michael, hopefully, are you in Texas? Are they having trouble? I saw something in the news this morning that the heat wave is pressing the power generation ability to keep up with demand in Texas. But yeah, total time, downtime. Yeah. Good. A bunch of different ones. One from the aviation industry was mean time between unscheduled removals. So it was, if you're doing planned maintenance, overhauls or updates or servicing, that didn't count against you, but only if something had to be replaced that you weren't expecting to be replaced. And so that was mean time between unscheduled removals was a common measure I saw. Years and years ago, a student handed me a military document that was a joint services one. So it included all 4 branches of the military and all of their acronyms for reliability and availability. And MT, add as many letters as you want, basically, was probably in there. And of course, the services had different definitions of what MTBUR was, and what they counted and what they didn't count changed pretty dramatically between the branches. And so this was kind of the Rosetta Stone of translating the measures and measurement systems by the different branches for availability and reliability. It was pretty fascinating. So one part that we have a problem with is, well, what do we mean? The customer wants it just to run. I want the system to be ready to go. When we push the button, it starts and we create widgets. For my car, I want it to start when I need it to start and minimize the amount of time it's in the shop. But that's not the same definition we use a lot of times in how we design and work for a product. And there's lots of reasons for that, but that's just one of the issues that I see as a problem between what the maintenance teams are facing at a day-to-day basis and the pressures they're seeing to get systems up and running and repaired quickly, minimizing mean time to repair or minimizing repair time, versus the design team that doesn't know what sparing system you're using, doesn't know what kind of tool sets you have, doesn't know what kind of training and capability you have. And it has to make a whole pile of assumptions around those aspects of it. So it gets fuzzy real quick between the two different groups, just on this simple definition. So now let's say you have perfect reliability, right? The product just doesn't fail. You make the product and it just runs and runs and runs and runs. And every time you want to go use it, it's ready to go. I don't know of any products like this. There's some that come close, like a crescent wrench. It's a pretty good product that, while it can be destroyed and actually fail if you overstress it or run an electric charge through it real quick and melt part of it. I've seen those things. Or if it's improperly sized for what you're doing, more likely you'll strip out the bolt, not the wrench. But I've seen some wrenches that have rusted and so on. So there are failure modes for them. But by and large, they're pretty reliable, right? I've got some wrenches that I've inherited that are probably on the order of 100 years old. Interesting construction and ideas people used for creating wrenches for unique situations. But even those, they need some maintenance, right? But if I had perfect reliability, I wouldn't need to make sure the rust was kept off of them and they were lightly oiled, which would be considered a maintenance role for even a simple tool like a wrench. So that's one scenario. I like looking at a formula or definition in the extremes. Now, the opposite extreme, and this one's you can do to scare your maintenance team, is say, all right, what if we make it perfect maintenance? If you had everything you needed to immediately, like in no time whatsoever, put a system back into service, like you were anticipating failures and you fixed it just as it occurred and got it up and running again. Well, the argument is that you don't really need a very reliable system. If it doesn't cost you any downtime to restore the system to full service, it can fail very often and it won't really matter. Now, both of those scenarios are kind of ludicrous, right? Yeah, ERCOT, the news this morning. I heard that they asked people to use less energy during the peak elements of it because they're getting really thin margin on what their capacity versus demand was. So it sounds like in the quick report I saw was that the system needs a lot of maintenance. Now, it probably worked fine for a long, long time. It was probably over-designed for what it was expected to need in the, say, 60s. But over time, and it's just like here in California with PG&E, there's a lot of deferred maintenance. And so there's anything but perfect maintenance in those systems. And they're struggling to recover from that and catch up and a whole bunch of other issues too. I don't mean to say it's just maintenance, but when lines are getting pretty old, it's harder for them to withstand the shocks that they're seeing these days. And that's a problem. So anyway, one way to look at the relationship between reliability and maintenance is when you put it into the availability equation and run them out to their maximums. And it comes back to that, well, what's the right balance, right? is we know that we're not going to make a system that has perfect reliability. And we also understand, or hopefully we all understand, that there's no such thing as perfect maintenance, that it instantaneously gets repaired and restored. That doesn't happen either. Now, there's the problem is that it's understanding where are we in that realm of when we design a product. And like oil change, I think many of you have experienced, if you're I don't know, if you have an electric vehicle, if that's the only thing you've ever had, you probably haven't. Well, I don't know. So I don't think that engine would have an oil piece on it. Maybe it does. I don't know. I don't have an electric vehicle. I remember my first car, it never really needed I was told by a shop that it doesn't need an oil change. And it was because it leaks too much and that you're pouring a quart of oil in it every week. So it's always got fresh oil in it. Don't worry about it. And then charge me a whole pile of money if I wanted them to go fix the leak. So that was a different problem. The idea, though, is and you've heard me say this before, any of you that have attended any of my webinars practically, is that reliability occurs at the point of decision during the design. It's what components we're using, what materials we're using, what configuration are we using, how are you going to assemble it, all of these different trade-offs and decisions that are made during the development process pretty much corral in and create what's its potential reliability performance in the field. Part of that equation, though, is that we need to understand the use conditions, which includes the maintenance scenarios that occur with a product. So if I'm designing a system and we want to create something that actually is useful and solves a problem for a customer or client, or is say a bottle filling device that works on a factory and it fills 100 bottles a minute or whatever its throughput is. That is not a trivial process. The same with these wrenches. If I could design a wrench that could take 100 times the expected load that I would ever see, as and I've seen people do this. They'll take a good sized wrench and put it on a bolt. It's all rusty and corroded over looking and stuff. Says, well, I need to get a lot of force on this. And then they'll put a cheater bar on it, a great big tube, basically, that sits over the end of the wrench and extends that lever that they have on it, sometimes out 4 or 5 feet. And they can really put a lot of force through that wrench into that bolt. And at what point do you say, we're going to design a wrench that can handle that kind of forces? Or are we going to use it as what's the length of this thing, and the engineering design, we can figure out what's the leverage of that and what's the strength of a strong person turning it, or using 2 hands or maybe 2 people. What kind of margin do you put in on this thing? And the same goes on a more complicated system like a vehicle, right? We can design it so that, like my early example of the early vehicles with, carried a whole bunch of stuff to do repairs, including patching kits, because you couldn't carry enough spares for any reasonable length of travel. And so people would take off the tires and patch the inner tubes and put them back together, and had a spare set of tires, maybe 2 or 3 strapped to the back of the car, and off they went. But tire technology has gotten better and better. The design of the tires have included metal belts that go in them and different resistances, even to the point where you can puncture it. And there's, I know that I saw this with mountain bikes at one point. There's some kind of chemical in it that when the air stream starts moving, it consolidates that metal or that material, this polymer, into the leak, and it binds it all together and seals it. So you can have a whole pile of punctures on your tire and it self-seals and you can keep going. Our designs have gotten better at minimizing, one, the chance of failures, but also the ability to heal or to recover from failures on their own by design. But all of those take a lot of trade-offs. Is, well, how long does it really take to change a tire on a mountain bike or on an early vehicle? Today, and I call AAA, and it's a matter of time of how long it takes them to show up so they can take the lug nuts off, because I no longer have the strength to remove those things. Either they're getting tighter or I'm getting weaker. I'm not sure which. But the idea is that if I'm designing these systems, is a factor that comes into it is, well, what is the capability of the maintenance groups and the people actually executing the maintenance to actually do the maintenance? Is it possible? Is it convenient? Is it routine? What kind of timelines are involved with that? If changing oil in your car would take you a week in the shop and cost $2,000, we would probably have a lot more pushback on the quality of our vehicles. Whereas if changing the entire engine was trivial, well, we could update our engine to the latest, greatest, and most efficient one or the fastest one or whatever every week if we wanted to. But those are both trade-offs of what's the likelihood of failure plus what's the extent or ability of the maintenance teams to do things. It's a factor in doing it. And so as you're designing a product, one of the things I'm always advising people to do is go talk to the folks that actually do the maintenance, the ones that are turning the wrenches, get them involved. Now, the reliability folks should have that conduit, should be the ones advocating for the design for manufacturing. Well, I'm sorry, design for maintenance. Manufacturing too, by the way, but if you're a repairable system, this is an important part of the trade-off system in order to minimize the downtime that you have, is because there's that factor of how long does it take to fix it. Now, one of the things I ran into years and years ago was a division of HP that made plotters, the great big 4-foot wide printers, basically, were very reliable. They were also very deep, very technically difficult to design and build so that they kept the print quality across the entire 4-foot span. And it was a marvel of engineering that they made these things that worked so well without having people have to do calibrations and everything else and do settings. And that team at one point was asked to design a high-speed printer that goes into the printing industry. So to print magazines, for example, or to print high volumes of stuff. And one of the issues they had was, given the increase in speeds and the amount of paper moving and so on, is that every now and then a piece of paper, if you've ever needed a printout real quick, you realize that paper jams, and paper in and of itself, even though a ream of paper all looks identical, they're not. Some are thicker, some are thinner, some have creases and stress built into them and so on, so that when they're moving through a mechanical device, they can crumple or bend or fold up or whatever. And so they had a failure where the paper itself, because of its variability, became a trade-off for them in design. And when it failed, it would do a lot of damage to the print heads that they were using. And so the issue is that they were trying to design this system so that it needed very little or no maintenance, much like the plotters. They figured, well, we can add toner or ink, and that's the only, add paper, and that's the maintenance you need to do. But they're going into an industrial setting, and they didn't come to they needed some help realizing that these folks have toolkits. They have skills and knowledge beyond just clearing paper jams. And so it was spending some time with their desired customers, focusing on how they went about troubleshooting, maintaining the equipment that they were currently using, opened their eyes to some possibilities in the design that allowed them to say, all right, well, if this fails, we want to make it so it's easy for the operator or the first level mechanic at that facility to execute the repair. And so that changed the nature of the design once they understood what the maintenance team could do. And it allowed them to get into that market because they were really at a trade-off they couldn't get a compromise on by making it so reliable, but maintain the functionality. And so it was an opening for them to improve this, to back off on the system reliability, counting on their ability then to minimize the downtime because of the local skills that were in those facilities. So hopefully that made sense. So one of the things I've run into is that design teams often really have no clues the variability of what does it take to get somebody out there with the right wrench to fix something, right? They say, oh, well, you just need to loosen this bolt and replace this component and then tighten it back up. You're all good to go. And let's say it's an oil pump on some device, on some system. Well, if you have to take the engine block out to get to that pump, that's not a trivial, in most circumstances and vehicles, that's not a trivial process and won't be done quickly. So hopefully the design puts it someplace that a person can actually reach with a wrench. And it's not a specialized tool. And they have those parts on stock or have availability to get them very quickly and so on. So there's training, there's processes in place to remove and replace and make sure it's secure, not leaking kinds of things. You have the right parts at the right time. Goes back into kitting and stock rooms and storerooms and supply chains. All of these things all have to come together for somebody to pick up the right set of tools and the right parts and execute the repair, the wrench time. But that's only a fraction of the time involved. The trouble with many design teams is that they only look at it as, well, what does it actually take, assuming you have everything in place, that you've recognized the failure all the way to diagnosing it and troubleshooting and understanding what repair action needs to be taken, to the time it takes to get the parts from the right person, to the actually doing it and recommissioning the system, which is a whole different set of variables that are often overlooked or overshadowed during the design process. So that's where reliability engineers working with their knowledge of the maintenance processes can help the design teams understand the total impact of saying, oh, they can just fix that, which sure, on the lab, on the bench with all the parts and tools right sitting there, it looks easy. Do it when it's snowing and you're in a side of a road someplace in northern Wisconsin. It's a different adventure. All right. The other thing design teams often do is focus on what are the mechanisms, right? How does it fail? If we've got either FMEA or HALT or all of the various tools that we bring to bear, or even just the general design engineering process of, well, how is this going to fail? What are the likelihood of this being overturned or stripped or bent or corroded or whatever? What are the failure mechanisms and stresses that are applied to it so that I can design a set of wrenches that can withstand the vast majority of all of these stresses for a long, long time? And so we get, plated tools and we get hardened steel, we got all these other cool stuff that does a pretty good job of being a wrench. Now, when it gets more complicated, there's a lot more trade-offs, right? And we often look at, well, what's the failures? Is it alignment? Is it the variation in the paper, and how do we manage and control that or minimize that variation? Different use environments, how do we make a product that's robust for that realm of things? But we tend to focus on Once we see a failure or recognize the potential failure, we often think about what's the underlying mechanism. And this is from a design point of view, and failure or reliability folks tend to help them think that through. Oh, this is a galvanic corrosion situation. We can't use these dissimilar metals in this kind of environment, and here's the mechanism. And then we redesign or fix that. The knowledge about failure mechanisms, in my mind, best comes from the people in the field. If you're fixing and repairing things and you are cognizant of the environment and use conditions that that particular system is seeing, and take the time to actually understand the underlying failure mechanism, which is a challenge in most maintenance worlds, that's invaluable information back to the design team. We can hallucinate all day long what we think the failures are going to be in the design world, but the folks that are actually doing the repairs are seeing all of the symptoms and all the circumstances right up front and right in their face. And they have a better clue as to what's the underlying failure mechanism if they're given permission and skills to actually identify them, right? So it's one of the big breakdowns in my mind is what is failing in the field, not just the symptoms, not the failure modes, but what's the underlying mechanisms. Now, I've run into some teams across my travels that are just excellent at it and have amazing feedback that is very, very useful and helpful back to the design teams. And they'll oftentimes resort to modifying equipment in order to minimize those failure mechanisms that they're seeing. And eventually the better ones will get that back into the designs of the systems that they're using. But that is rare. It's rare that the maintenance teams will dig deep enough into the failure mechanisms in order to advise the design teams how to make a better product. And it's a two-way street. A lot of times the design teams are maybe not consciously, but don't want to hear from the technicians. And I think that's a bit of misguidance. There's a wealth of information there if we learn how to talk to each other on that area. All right, well, let's switch over to how the design actually impacts the maintenance side of things, the maintainability side of things. Now, the maintenance teams, by and large, and I'm grossly generalizing here because there's teams with all kinds of different focuses and talents and skills, but by and large, the teams I've run across that are executing the maintenance on a system really are trying to minimize time to repair. If they're well run, they are following their directives of that operations manager or of the garage that is repairing cars is, let's turn around these quick so that we can send the invoice out, or we can create more products, or whatever it is that system or garage is doing. And time is often a critical piece of it. So systems are set up so that the right tools are in the right place, and we have enough spares to not have to go waiting for parts or special cases. We don't spend a lot of time doing diagnostic work for tricky ones. And I've seen too many teams that don't even think about diagnostics. They just do shotgun. Well, if it's not doing this, that, and the other, I'll just replace everything. Yeah, the failure analysis stuff. It's not always, if it's almost should be a meme, and I think it is in a couple of cases, but you've run into it where the factory line is down and the maintenance team sitting there taking it apart, this piece of equipment apart, trying to figure out what to fix, what caused the failure. And there's some yahoo in a suit standing there tapping their feet going, hey, how come it's not running? And the idea is, and I think it's admirable and I think justified for maintenance teams to figure out, well, what actually caused the failure? So actually fix the right thing. All right. Because if I put some baling wire on it and keep it running, I'll be back out here in a half an hour. Or I'll fix one possible scenario for what caused this symptom, and it may or may not be the right thing. And I could spend a lot of time guessing at what should be fixed. Now, with experience with particular equipment, some mechanics can tell pretty quickly that it's likely these three things. I'll replace those three things and they're off and running. But that's also pretty wasteful for resources and time, and also what information comes back. Is it one of these three parts that failed, or did all of them contribute to that failure? So if I'm looking back as a reliability engineer, what was replaced, I get a very unclear picture of what was the underlying problem. And so some maintenance teams do that extra step and say, all right, we need to troubleshoot this and figure out what actually failed, not just to get us back up and running more efficiently or more secure, confidently, but also so I can feed it back into the system, so we have the right spares for what's causing failures in the right system in place to redesign this out. If we don't identify the issues, we're going to keep facing these. And so the better teams do take that extra time to go about doing it. Yeah, the Band-Aid approach, exactly, Carl. The better teams avoid that, but they also have permission to do it. They don't have somebody saying, hey, get the system running. They understand the longer term value of doing a proper fix, plus extract the information so that we can systemically fix it. But by and large, vast majority of teams are focused on just, let's turn this around, let's get it fixed, and have their fingers so close to a lot of really good information, but either unwillingly or are told not to pursue that information, which would be invaluable back to the design or long-term fixes. So that's one issue that is a dynamic that plays on the maintenance teams. A common metric is time of repair, right? How close to actual wrench time, the theoretical just do the fix, can you get? So let's make sure we have all of the proper systems there, and equipment in place, and training in place, and tools in place, so that you can fix it very quickly. In getting as close to that theoretical, just pure wrench time as we can get. And then even then, you're trying to do it faster. So I'm sure you've all seen video of NASCAR or Formula One coming into a pit stop, and a whole team of people change all the tires, add fuel, add oil, clean the windshield, do it like 47 things in 15 seconds or less, and the car's back off and running again. It's not the same as the old mechanic that would, grab the distributor cap and just by ear or by a strobe light figure out what the timing should be for this, or set the timing for this distributor system for this old engine. I actually did that when I was in the Army. On the Jeep I was in charge of driving and maintaining. Not a quick process, especially somebody that doesn't really know what they're doing, but that's what they asked me to do. Time to repair matters in some places, and time is of the essence in some places, and there's good economic reasons for that. But being very clear about that and setting up systems and programs in place so that can happen is critical. Now, the design team has a huge role to play in that, right? Those Formula One cars and NASCARs are built to have all four tires replaced almost instantaneously, those kinds of things. They are built and designed with the understanding that the time in the pit stop matters. And so they are optimized to minimize the time of repair. Now, my vehicle sitting in the driveway is not. It's not meant to, for whatever reason, anytime I take it to a shop, it's going to be a minimum a couple hours. There are the quick oil change places that say half-hour oil change. When pressed why my vehicle is there for an hour, they said, well, we only have 3 bays. You're the fourth one here. So the half hour was taken by the three that got there before you. And it's like, okay, so the half hour is wrench time. The half hour is not waiting time for resources. And so it goes. But anyway, the design of the system affects what you can repair. And there's always a trade-off. What is likely to fail? What needs regular maintenance? What are those trade-offs? What needs to be easy to get to versus what can be more buried? And it may double the repair time, but if it happens infrequently, that might be a proper trade-off. Now, part of this knowledge comes from actual good field data. Going back to that shotgun approach that Carl named appropriately is, or the Band-Aid approach, is if I just replace 10 different things in the hopes it fixes something, and I report that I replaced these 10 things without the information about which one actually made the repair, because that wasn't part of the process, then we're kind of in a bind from a design standpoint. Is, well, what's involved in this failure mode? It really clouds our ability to understand what is it that we could improve so that the repair is quicker and easier. And replacing 10 things might mean, well, let's just make that one replaceable unit, make it one bolt, and all of that stuff comes out and all of it goes in. And if any of those 10 things fail, then we get it all with one quick operation. Now, that may or may not be feasible for your system, but it also might be very expensive. And so that's a part of this feedback mechanism between the two groups, is getting, well, what actually failed? And some of our, well, and I kind of foreshadowed myself here, is the, sometimes, especially, and I ran into this more in military systems, is the idea is that if I have a, say, a communication system of some sort, if I can replace the whole box on the, if I get a new radio and I take the old one out, put the new one in, and I'm up and running, I can execute that repair real quick. But if I had to open that box and check all the vacuum tubes and replace the individual components or circuit boards, or run diagnostics and get my oscilloscope out and do all this stuff when I'm in the field, it would take way too long, and I probably didn't have the capability out there in the field to go do that. And so this replaceable unit, if I can replace the entire box and send it back somewhere else for a more detailed repair, is a pretty good idea to keep your system up and running. It's part of a design process, though, is where are we going to do the repairs? Who's allowed to open the box and has the right tools, equipment, and so on? Recently, Apple announced that they were opening up repair centers where they had all the unique tools you needed to open up your iPhone or your laptop, and you could replace hard drives or batteries or stuff like that. Now, apparently, the individual components were priced pretty high. No surprise there. And access to all these unique tools, some of which required a bit of understanding how to use. So there was some training and some coaching available there. So the service was not inexpensive, because it did cost Apple more to help you do the repair than if they just did it themselves. And so there was some, I don't know exactly why it was done. Maybe it's part of an experiment to let people do their own repairs. But the idea is that instead of replacing the entire phone, if I just need a new battery, I could go to the shop and do that repair myself. And the idea being, I could get it back, that I could keep my phone in my possession, and it'd be out of commission when the battery's out of there, and probably out of commission the way I would put it back together, because I don't think duct tape holding the case together is what their design intent was. But the idea would be is that I could do it myself in a couple hours, as opposed to drop it off at Apple and they're quoting 3 days where I'd be without my phone. So there might be some expected value for that kind of process. But the inside of a phone is pretty darn complicated. And so there's lots of things that can go wrong. And so maybe that's the case. If I really depend on my phone for my business, I'll just get a new phone and, recycle or donate the old one. But that's a trade-off every one of us has to play for our communication devices or the systems that we're building. And so what is the importance of the economics of avoiding downtime, say in a factory? And can I design my system so that I can replace modules that only require simple tools and can be executed quickly? And then if I have repair facilities, maybe in that shop with more specialized people doing the internal repairs to put it back on the shelf, that could be an economical advantage. And both for minimizing downtime and minimizing cost of spares, because I can do the diagnostics offline, downtime is minimized on the production floor. But that's a design trade-off. And is it in concert with what's the skills and capabilities of the facility and their importance of maintaining the system in an uptime state? So a whole slew of different trade-offs that get involved there. All right. So I don't think I actually answered this question at all. So what are your thoughts? What does the design team need? What is it as part of the engineering requirements package? What do they need in order to get this balance right? What are some of the factors or considerations there that maybe I sparked some or you're familiar with already, but what would they need in order to get this balance of uptime correct? Yeah, all the trade-offs, but this is, cost benefits, but from whose point of view, right? I can create a very simple system that's very difficult to repair, and that benefits me in my manufacturing or in my design process. So how would you expand that, Carl, to what's the cost benefit trade-off encompassing what? Yeah, Michael, the appropriate users and players. Yeah, the stakeholders, another term I would use. But the idea is, what are, and especially if you're doing factory equipment or, let's use vehicles. I've been using that example all the way through. I mean, it would be there's a range of different types of people that own vehicles. I have a neighbor that likes doing his own oil changes and all kinds of simple modifications to his own car, and will buy the parts and replace things himself when he can, and reluctantly takes it to the shop. Where there's other people that will just buy the service plan and take it to the shop when it's needed and take care of it. But their need for their vehicle as an availability issue is not as high. So there's a range of stakeholders just on customers, but there's also the garage and shop owners, the dealers and those folks. Marketing might be involved with this kind of a discussion. Let's see, I think I missed one here. Carl's talking about, I think you brought it up earlier, is the planned obsolescence. Given the changeover of components and parts and pieces and so on, and the dynamics of the industry and the economics of all the component makers, I don't think we have to worry about planned obsolescence. I think it gets forced on many of us, whether we want it or not. Yeah. Good one, Carl, is all the asset management considerations, which is more than just maintenance. It's also the economics around the equipment that's in your facility, and includes its total life cycle costs. And so I once learned that a helicopter, and I always knew that military vehicles had a huge very expensive and long-tailed support packages that went with them. But a helicopter needed, for every hour of flight, it needed like 30-minute or 2 hours of maintenance. It just seemed out of whack to me that, and then they explained it is that a helicopter is, 20,000 loosely affiliated components flying in formation. And then after sitting on a helicopter and, bolts are backing out of little screws holding the sheet metal on the inside of it, were backing out and falling onto the floor and then out the back door. And hydraulic fuel was dripping on us. But I was glad I had a parachute on and we were there for a sport parachuting. So I was glad I was leaving the vehicle after seeing all this stuff happening when I'm sitting inside of it. But it flew that mission and flew a bunch more flights for us so we could jump out of it. But that was when asking the pilots about it. Oh yeah, that happens all the time. And they just fly on. Let me see a couple other ones. Yeah, in locomotive design, you're talking about it, those are all the folks, in my opinion, know what's going on. And hopefully they have the capability, Michael, to actually provide enough information, not just general symptoms, but when given the chance to say, no, look, this thing fails and it takes us 2 hours to even get to it. This is very hard to diagnose. Or if you get good information from those folks, which they have to be allowed to gather that information, I think then it works really, really well. So that's great. You're getting a chance to talk to those folks. Yeah. One of the things, Nelson, I've learned years ago is that the smaller companies and the smaller shops are much more, well, agile is one word for it, but flexible, but they're also still learning, right? And they don't get to a point where, hey, you take our product or not, or don't take our product. We sell enough that it doesn't matter. Kind of attitude. The small companies want to create a relationship. And part of that relationship is actually listening and responding to what they're hearing. And so there's all kinds of good things that can go with just exchanging information. That is one of the things I ran into at HP. I was on a trip to a supplier with my boss, and he was just, every sentence was, how are you going to reduce costs? And the message was clear and simple: reduce your costs, or else we're going somewhere else. And I'm like, aren't we here to actually help them get their line up and running so it meets our standards, because we need the capacity? And he goes, but only if they do it cheap enough. I was like, do we really want a company supplying us that is having trouble meeting our quality standards, and you want them to do it cheaper? It's like, I think there's a dilemma here. I don't think you're actually being helpful. He didn't seem to like that a whole lot, so I wasn't asked to go on any more trips with him, but that's the way it went. But smaller companies are often very willing to work with you, and in order for them to gain knowledge, to have a more stable supply chain relationship with you, all kinds of reasons, and or to maybe find a proprietary design that meets your needs uniquely, so then you get locked into them. There's all kinds of ways that, other than just price, that you can work with suppliers. Yeah, Nelson, I'm seeing more and more of that over, even the last 20 years. It's there was a TV commercial years and years ago, and I don't remember what company was doing it, but there's a person or a woman standing in a kitchen, and somebody's knocking on the back door, and she opens it up, and it's like the Maytag repairman. It's a repair person with a little toolbox, and says, I'm here to repair your refrigerator. I didn't call a repairman. And he said, no, your refrigerator did. And we're getting more and more of that. I think Tesla sends all kinds of interesting information from their vehicles back to the mothership, basically. And I've run into people in conferences that are working on all of this information that's gathered by your vehicles on use conditions, on wear rates, on how sharp the loads that are put on the springs when turning a corner at speeds, and all kinds of weird stuff. That allows the design team to get a whole different picture of what's the distribution of stresses and behaviors that occur to a vehicle. And a lot of that information is getting out there. The better we get at understanding failure mechanisms and the symptoms they exhibit prior to causing a failure, the predictive maintenance kind of approach gets designed into products, the better. It addresses certain kinds of failures, not all of them. If a tree falls on top of your car, it's not going to be available, and there's not a whole lot of time between the first cracks of that tree and when it lands on it. So there's not a lot we can do in the design for those things. But you get the idea. Yep. And see. And the other thing I run into, Nelson, on years ago at HP, one of the marketing requests, and allegedly, I never really knew what marketing did at that time, but allegedly it was customers wanted to be able to print faster. We're making inkjet printers, so the ink had to actually dry. So if you print one page and you print another page too fast, the ink will still be wet. And so you're putting a piece of paper on top of wet ink, and you get a mirror image basically on the paper on top, which isn't desirable. And so part of printing is, and you see it on printers, as they will even though the mechanisms could crank out paper way faster, because if you print very little on a piece of paper, it comes through there really fast. But if I do full page print and then there's another page right behind it, it slows down a little bit, right? You're printing something that has full print and then the next page has very little on it. It could come out really fast, but it doesn't. It holds a delay so the ink can dry. And so one of the ideas way back when is that if we could measure the humidity in the room of that area right around this paper, which is correlated to how fast the ink dries, we could adjust the speed so that if you're in a dry environment, drier than our assumed, outdoors in Singapore or Houston, which is usually high humidity, which is kind of the worst case, is then we could shorten the delay. And the issue is that the humidity sensors at that time were 1-inch square bricks, basically, that were used in HVAC systems. And so now you can find a humidity sensor that's very, very small and accurate enough to adjust print speed. But that didn't exist when we first went looking for it. And so a lot of sensors, a lot of technologies has gone into making the instrumentation of our equipment possible. But it has to be tied to something like, we want better print speed. If we knew the humidity, which is the gap we have, then we could adjust for that. And so that became a connection to a failure mechanism, and that phenomena, the physics or chemistry that was occurring. A lot of teams just kind of skip that part, and they put instruments and widgets all over things. And so it senses when it's down, but couldn't tell you what. Or they give you the always useful, well, that was error number 64. And okay, why don't you just tell me what it is rather than making me go find a book someplace? But I digress. So Carl, on the artificial intelligence one, that may be a whole new webinar. I do have an opinion on that one and plenty of thoughts. And I've been approached by a handful of companies over the years to help populate, or train these kinds of systems or interpret those kinds of systems. But yeah, so I've got a little bit of thoughts on that one, probably an hour's worth. So anyway, thanks so much for hanging out and participating and taking a look at this interplay between maintenance and our design process. the bottom line is that it's a two-way process. We got to talk to each other. And I believe that the better systems and better designs of products that we have get maintenance folks involved early on and listen to them, and then vice versa. Maintenance teams are given permission and encouraged to gather the relevant information and know what to gather and execute excellent repairs. So I think it has to go both ways in order for us to get the uptime that we want and desire for whatever systems that we're putting out there or using. So once again, thanks so much. I think next month I have a guest webinar presenter. He's and I'm drawing, as usual, drawing a complete blank on the topic. And I'm drawing like 2 weeks from now will be Chris Jackson. And I think he's talking about confidence and reliability. And he always has an interesting take and a way of presenting that. So I'm looking forward to that one. And have a the rest of your Tuesday. Hope it goes well. And we'll see you all in a couple of weeks. Oh, I do have a thanks slide on this one. Cool. All right.